Welcome everyone to this week's M2D2. This week we have Tinglin Huang, who's a second-year PhD student at Yale, advised by Prof. Rex Ying. His research interests include computational biology, geometric deep learning, self-supervised learning, and AI for health. He previously worked at the Broad Institute and Tsinghua University, and today he will present his work on exploring the relationship between molecular datasets and machine learning. That was published at NeurIPS this year. So thank you.
Yeah, thanks for the introduction. Yeah, hi, good morning, everyone. I am Tinglin Huang, and thanks for this opportunity to speak at the reading group. And today I will be talking about our work on investigating the relationship between different molecule datasets. Um, and in the biomedication fields, like predicting the properties of molecules is really important, like such as the toxicity and the solubility. Machine learning is now a very powerful tool in this field. So basically, given the molecule structure, we will use a machine learning model like a graph neural network to predict its property. Um, but one challenge is um, we don't have too much data because labeling a molecule is very expensive. So here are four example data sets from the MoleculeNet. Like for example, for the clean tox, which is like a clinical toxicity-based data set, and I mean it only has 1,000 label instance, and the FreeSol only have around 400 label instance. And and in our papers, we study a new strategy to improve the performance of the machine learning model on such a molecule data sets, which is to collaborate with the some additional data sets, and we call them the auxiliary data sets. So here is an illustration. So the main idea is, given a targeted sets, which doesn't have too many molecules, I mean the label molecules, and we combine these data sets with the with multiple auxiliary data sets. So it could be a larger data sets, and we hope that these additional data sets can transfer some useful knowledge or out of distribution knowledge to the model, so it can have a greater performance. All right, um, and here we wanted to highlight that I mean this strategy um, can be demonstrated by the other domains, including the multitask learning and the transfer learning, which also try to improve the performance by incorporating more, I mean, additional information. So, but there is a challenge that the negative transfer can, I mean, sometimes occur when combining multiple information together. Yeah, because sometimes I mean the knowledge in one data set may contradict that of the other data sets. So in our paper, we first do an empirical study to verify this phenomenon. So basically, we collect 50 molecule. We have 50 molecule data sets from the MoleculeNet, and we consider the 11 small data sets as the target data sets. And we will evaluate the performance by pairing the target data sets and the other auxiliary data sets. Um, so here is the so here's the architecture we use in this study. Like given a pair of data sets, one is the target data set and the other one is the auxiliary data sets. We will use a specific decoder for each data set because they have they have different tasks in each data set. And I mean, but the encoder is shared across different data sets. Um, and and here we use the GIN as the backbone model. So um, so here is the result for this preliminary study. Like the reg block, I mean the reg cells means that the target data set have a greater performance when combining with the auxiliary data sets, and the blue cells indicates that it is the negative transfer case. Um, and we can have some interesting findings. For example, we can find, for example, like let's take a look at this pair. We can find it as an auxiliary data sets. The TalkCast can greatly improve the performance for the clean task, and it is reasonable because they are all toxicity-based data sets. And there are another finding. For example, like we can find that the relative improvement is not symmetry. Um, yeah, which means that maybe one data set can help with the other data sets, but conversely, that data set might not be very helpful for that data sets. So, and I mean, this result also verifies that there is a affinity distribution among different data sets. Um, so furthermore, uh, I mean, with these experimental results, we wanted to ask a question that is, how can we measure the affinity of a auxiliary data sets to a target data sets? And here we investigate the relationship between different data sets in two dimensions, which are the structural characteristic and the task information. And we use and specifically like given one data set, we will use task to vector to extract the task embedding to represent its task information. And and we will also extract the fingerprint feature for each molecule in these data sets. And then we can obtain a fingerprint distribution by averaging all these fingerprint feature. Like fingerprint feature is like a multi-hop vector, um, and each bin represents a substructure in the molecule. So so basically, given a data set, given one data set like the clean toss, free sol, whatever, we will use the task to vector to extract the task embedding, and also we can obtain a fingerprint distribution to represent the structure characteristics. So with these two techniques, like given a pair of data sets, we can measure their task and structure similarity. So like here's an illustration. Given one data set, we can extract its task embedding and fingerprint distribution, and we use the KL divergence to calculate their task or structure similarity. So so building on top of this, we can try to answer that questions. And here we measure the Pearson correlation between the relative improvement of all pairs and the similarity measurement of all pairs. Um, so which means that a higher correlation means that the structure the structure or task similarity can mm, similar structure or task can have a greater performance. So here is the result. Here we also use the combination of the structure and task similarity. And here we plot the regression curve. And we can find that the combination of the task and structure can have a greater correlations. Oh, here I saw someone raise their hand.
Yeah, sorry. I've a question here actually about the result. If you look at the structure plus task plot, it seems to be almost bimodal. Like all the top ones have like not much slope, and then the bottom like left diagonal has quite a slope.
Uh,
Do you know like what those dots correspond to?
um, yeah, because there are some data. Let me go back to this result. So I mean, that slot maybe represents some cases that have very strong negative transfer phenomena. For example, like in this row at the base, they
Hmm.
almost have the worst performance when you combine it with the other data sets. Um, and yeah, hopefully I can answer your question.
Yep. Thanks.
And yeah, so in this So in this result, we can find that we find that the combination of these similarity can be a better indicator to the relative improvement of the pairs. Um, and here we focus on the individual data sets because different data set might require different information. And, and here we calculate the Pearson correlation between the relative improvement, of all pairs between the target data set and auxiliary data sets, and the similarity measurement of the pairs between the data sets. So here are the results. And each bar represents a correlation, and a positive correlation means that um, I mean the auxiliary data sets with similar structure or task can have a better performance. Can bring a better benefit to the target data sets. Like for example, for the clean toss, you have a very high. You have a very high positive uh, correlations. And the negative correlation means that maybe this data set requires this similar structure or task, for example, for the cider. So we can find that maybe this data set requires out of distribution knowledge. So in conclusion, like both similar and this similar structure and task can potentially benefit the target data sets. But it depends on the target data sets. And another interesting finding is these two information are compensatory. Um, so which means, like for example, for the TOS 21, we can find a very weak structural correlation, but you have a strong task correlation. Um, I mean, um, with the relative improvement. So which means that maybe these data sets requires the auxiliary data set with a similar task information. Maybe it requires maybe the other data set with the similar task, like also the toxicity-based task. So, um, so overall, so here are some takeaway messages. Um, so like with these experimental results and analysis, we want to ask like if we can design a machine learning model to automatically select the auxiliary data sets, which can maximize the performance of the target data sets. So that's our focus. Um, So here we define this problem as the auxiliary dataset grouping. Formally speaking, given the target datasets, and we also have a set of candidate auxiliary datasets. And what we do is awesome. Yeah. And what we do is we will try to use a machine learning model to select a subset of the auxiliary datasets, which can maximize the performance when we combine them together. So it is similar to a multitask learning. Which means that we have a multiple data set and each data set have different tasks. And in our in this setting, we will do balance sampling to form a mini batch, and we will average the loss to optimize the model. All right, so here in this paper, we propose to use routing mechanism to quantify the affinity between different data sets. So here are three situations for the knowledge transfer. Um, so on, on the left-hand side, yeah, we can see all the data sets are shared together with, uh, all the parameters are shared together, which means that they share all the knowledge in one model. In the right-hand side, there is a all specific situation, which means that this data set doesn't, they don't share any parameters. And so they cannot transfer any useful knowledge across them. And in the middle of them, there is a mixed model situation, which means that each data set have their each data have their specific and the shared parameters. Um, and intuitively, we believe that for a positively transfer pair, um, like we hope we hope the parameter could be more shared. And for the negatively transfer pair, we hope the model can be more specific. Um, And here in our paper, we propose um, to use the routing mechanism to routing function to determine such a relationship. Like so, so here is a so here is an illustration. Um, we assume that we have m datasets, like including one target dataset and m minus one auxiliary datasets, and we will assign um, I will assign different parameters for each dataset. Um, and we use the theta to denote the data to denote the parameters. I mean, so in the routing mechanism, so here in the in the original layer, um, we just feed the mini batch of one data set and we obtain the representation in each layer. But in the current layer for the auxiliary data sets, we I mean for the forward process of the auxiliary data sets, we uh we not only use their specific parameter, we also use the target data sets parameters. And we use a routing mechanism to balance these two outputs. So basically like given the input of the representation for the auxiliary data sets, we will use the target data sets parameter and also use their specific um, parameters to calculate the output, and then we use the routing mechanism to balance these two results. Um, so so intuitively, like we this routing mechanism can enable the model to determine the impact of one auxiliary data set on the target data set's parameters. Like um, so here are two situations. Like we can find that like higher gating score means that like the model in the routing mechanism encourage the model to use more target data sets parameters. But a lower one means that the model just the lower one means that the mo I mean each data set tend to use their own specific parameters. So we believe this routing mechanism can enable such a flexibility to quantify their affinity. Um, and motivated by our preliminary studies, we believe that for the task affinity, believe that the gating score should consider the task affinity and the structure affinity. And for the task affinity, for each data set, we will assign a learnable embedding. And for the structure affinity, we will use the fingerprint feature and use the set to set to, to obtain a structure representation. And we will calculate the task affinity and the structure affinity and combine them with hyperparameters. Um, but there is one problem regarding the optimization, because in the original optimization framework, uh, like it only optimized the model towards minimizing the loss of each data set. But what we want is we want to optimize the routing mechanism towards minimizing the target data set's loss. Um, and we also hope that after the training, the auxiliary data set with the high affinity should be assigned a larger gating score. Um, so um, and so in our paper, we propose to optimize the routing mechanism by a bi-level optimization framework. Like we break the original optimization framework into two steps, into two levels. So in the lower levels, we will first optimize the target, a given mini batch from target data sets and auxiliary data sets. And we will first optimize the target data sets parameter with the auxiliary data sets mini batch. Then we can, and here we use the theta t alpha m to denote it. And with these updated parameters, we will retain the calculation graph. Then we optimize the routing mechanism based on these updated parameters. But this time we will use the target datasets mini batch to calculate the loss. So in this optimization, like we, I mean, the routine optimization for the routine mechanism is um, sorry, I mean the routine mechanism is optimized towards minimizing the target datasets loss um, so that we can have a like so, um, so we can optimize the routine mechanism in the with the desired objective. Um, all right. And so here is the overall pipeline of the MolGroup. Like the main idea is we try to quantify the auxiliary, sorry, we're trying to quantify the affinity score as the gating score. And the way we make it is using the routing mechanism. Like routing mechanism can enable the model to quantify the impact of the uh, of the of the auxiliary data sets on the target data sets. So so in so the in this setting, the input will be the target data sets and a set of candidate auxiliary data sets. And we also will have a threshold for filtering the data sets. And and the selection process will be an iterative filtering process. Like like in the first step, we will try to initialize the model with the routing mechanism, and we will train the model on all of these data sets, and we will update the routing mechanism with the proposed I mean the bi-level optimization framework, and which means that we will optimize the routing mechanism with the updated target parameters. Then after um, after training the model with a few for a few epochs, then we will filter out the data sets according to their calculated routing. I mean the calculated gating score, and um, and we will repeat this process until we have the top K auxiliary data sets. So here is the our proposed framework. And so here is the benchmarking. So we uh we we compare our model with the other baseline on 15 molecule data sets, and we consider 11 of the as the target data set, which has the limited number of the molecules. And here we consider the molecule. Oh, sorry. Here we consider data sets with 11 with less than one sorry with less than 10,000 molecules as the target data sets. Um, and the setting would be like given the target data sets and we consider the other data sets as the candidate auxiliary data sets, and we will let the model to select the auxiliary data set and evaluate the performance when they train together. And the backbone as for the backbone, we use the GIN and the pre-trained graph former. And for the baseline, we have three kinds of baselines. I mean, for the one is the search base, which means that we just consider the all pairs of the data sets um and train the model for a few epochs and conduct a selection based on the performance. And then another baseline is about a grouping based method, which is like a um I mean there is some previous studies working on the multitask learning grouping setting. And the last baseline is about the multitask learning method, which means that they will try to propose um like a like a like a um, like a balancing loss uh, algorithm. And so here is the result. Yeah, we can find that the MolGroup can consistently improve the models on all the data sets. Um, and we can also find that it's really it's really hard to improve for performance. For one data set, it I mean given one data set, the negative transfer can always occur. You can see it's hard to find a really consistent improvement for other data sets, for the other method. Um, yeah. And here we want to show some really interesting result based on our method. So, um, so here visualize the selection result as a bipolar graph. Yeah, you can see like in the left-hand side is the auxiliary data sets, and in the right-hand side is the target data sets. Then each edge represents a selection. And here we visualize the top three, here we show the auxiliary data set with the top three affinity scores. And here we can find that. Here we can have some interesting findings. For example, like we can find the PCPA is the most famous one. Yeah, it has I mean five of the target data sets select the PCPA as the auxiliary data sets. I think and it's reasonable because PCPA uh, has the has the diverse molecule structure, and also he has many diverse tasks. And also we can find that for the TOS21, as an auxiliary data set, you can benefit the clean talks and the talk cast. And it is also reasonable because they are all related to the toxicity. Mm, and another finding is like we also find that the data sets from the different domains, but it can still benefit the other data sets. For example, for the Q&A, Q&A means the quantum mechanism. It can still benefit the BBBP, which is related to the bioactivity um, molecules. And also for the ESO can benefit the lipod. Um, and so we also find that the PCPA is a very effective booster. So here we do an analysis. Oh, so here we do a do a evaluation on this. Like we we evaluate the performance. We evaluate the performance on of the target data set. We also pair the target data set with the PCPA, and we see the performance. Um, Here we can find that the PCPA can always boost the performance of most of the small molecule data sets. And yeah, because the PCPA has the most number of the molecules with diverse structure and the task. So that's reasonable. And another interesting finding is we find that um, I mean we grouping more high affinity data sets can improve the performance. So like for example, like here are eight data sets, and when we try to combine more data sets, the performance can consistently be improved. Yeah, so here we're going to show that the MolGroup can provide some very interesting result. So oh yeah, all right, and that's all about our paper. Like so in our paper we study a problem that's called auxiliary dataset grouping. So given one target data set, we want to ask a question that is how to identify a good subset of auxiliary data sets which can maximize the performance. And in our paper, we did some preliminary analysis. We try to analyze the relationship between different molecule data sets from the structure and task dimensions. And also we propose a method called MolGroup, which is a routing mechanism, with a routing-based grouping method. And yeah, and I think that's all my presentation. Um, Here I can see some questions. Um, where the target? So here is a question. So here is a question about like, do we have an ability study showing where the target
I
or
can I can jump in and repeat the question. So I was just wondering whether you know if the target similarity or the input similarity is leading to the routing or is something else.
target or sorry, what do you mean by the target or the input similarity? The similarity is measured between two data sets. Let me see. Maybe in this slide. Uh, Let me see. Um, I'm, not- I mean, the similarity is measured between the target data set and the auxiliary data sets. Um, so um, so sorry, I don't really get that problem.
So basically here, the routing is decided by passing the data from both data sets. And there's a network that decides whether alpha equal to 1 or 0, right?
Yes.
Okay, and so basically we don't know what, like, unless I've missed that, we don't know what exactly the network is relying on to make that decision, or whether it's 1 or 0. It's just making the decision that improving the performance the best, right? So I was just asking, for example, if you were given to das routing a network, only the input, only the molecule from both data set, or only the target from both data set. Would that change? I'm guessing that will change the outcome of the routing.
Um,
So, and that will give us an idea of whether is based on the input or based on the target that the routing is on.
yeah, the input will be a pair of the mini batch from target data set, that's BT, and the main auxiliary data set, that's the BM. The input will be a pair. I mean the affinity is is measured towards the um I mean it's measured between these two data sets. So um I think the I think the most important factor that contributing to the gating score is uh so yeah, I mean here is the how we calculate the calculate this gating score. Like we use the task affinity and structure affinity. So mm, so I think the yeah yeah, I try to answer the question, like hope they can help, like I think for the routing for the gating score, the um in my I mean the task affinity and the structure affinity uh will dominate the gating score calculation. So um yeah, it is case by case, like given different target data sets, like given different target data set, maybe maybe the target data set requires different I mean the similar or dissimilar structure, but it is case by case. Um yeah.
Yeah, cool. Completely makes sense. Thank you.
There's another question in the chat.
Oh yeah, someone is asking if we can use data set of log S values molecule with high, is there any chance that subset of you can be helpful? If we Oh yeah, that's an interesting problem. Like um yeah, right now we are trying to conduct a selection on the data set level, but I think maybe we just need a subset of the data set. That would be very helpful. And I think it's a very interesting direction. And I'm actually I am working on that currently. Um I think very interesting because molecule um because given one molecule data set, we can also cluster the data set. I mean, the cluster the instant in this data set with according to their structure, according to their structure. Um, so we can also split one data set into multiple small data sets, and maybe different small data set can also be beneficial. If we can remove the information that could be harmful to the target data sets. I think it's a very interesting direction. Yeah. Um. Yes. And another direction is like because one molecule data set could have multiple tasks, so maybe we can also do the splitting on the task dimension. Yeah, so that we can have a finer data set. So yeah, I think you can enable I mean the flexibility for larger range of selections. Yeah, that's an interesting direction, I think.
Okay. Any other questions from the audience? That I have a few. First, I was wondering if you tried to do like single input routing, right? So
Uh,
learn, yeah, go ahead.
you mean like a you mean remove the target data sets information?
Yeah, instead of relying on like the whole batch to make a decision, just rely on a single example and then
Oh,
use,
yeah, we have tried this, but one problem is it's not really stable. Like because maybe one molecule mm, yeah, because we are trying to measure the affinity for the whole data set. So maybe case by we have tried that actually, but it's not really stable.
yeah, I guess you'd need to use something a bit fancier like reinforcement learning.
Yeah.
Um,
Mm-hmm. Um,
yeah, cool. And I guess my other more open-ended question is, given all that you've learned, if you could ask, a pharma company to generate more data, what would you ask of them?
yeah, that's true. Yeah, that's true. Yeah, also give some direction, right? Like how to generate some useful data sets. Yeah, maybe in this task we require some data sets with more similar structural tasks. Uh, yeah, I mean this we believe the MolGroup can provide such insights.